It's a great pleasure to introduce Professor Nick Rozenblyum, who will be speaking on the moduli space of local systems.
Thanks very much. So I guess the goal of this talk is to describe various ways of parameterizing, building parameter spaces of local systems. But I guess I wanted to start with a little bit of context of kind of why bother. And the motivation, at least in this work, was from Langlands. So there's the Langlands correspondence. The relevant version for this is that suppose I have a curve, projective curve over a finite field, and then the Langlands correspondence, whatever it is, predicts some sort of correspondence, ill-stated, it's the way I will say it, between kind of automorphic functions for a reductive group G and Galois representations from in this setting, what I'll call the arithmetic fundamental group of X into G. So as stated, there's no, anyway, draw it more squiggly to indicate the vagueness of this assertion. So I don't want to, so the bulk of this talk will be about this right-hand side. But I want to first motivate the idea of looking at this right-hand side in this way by looking at the left-hand side. So one thing that's specific to this setting that's a very fruitful idea is that whatever this is, the space of automorphic functions, this has a, using the fact that, using this geometric set, in this geometric setting, this has a very nice interpretation in terms of algebraic geometry. Namely, we can form I guess the favorite object of this seminar, which is the moduli stack of G bundles on X, and take the FQ points on this. And this is the space of compactly supported functions on the FQ points of this stack. And so the point is, well, what's nice about it is that you can try to study this by studying the algebraic geometry of this modulus. In particular, I don't know if this has been discussed, but there's a way of producing such functions out of what's called a function sheaf correspondence. So if you have an étale sheaf on BunG with extra structure, there's a kind of a way of producing a function by the function sheaf correspondence. So that really uses the structure of this as an algebraic stack, and in particular, such a thing produces you functions not just for on FQ points, but on FQ to the n points for all n at the same time. So anyway, so I don't want to say anything about that other than to point out that kind of two things. One is that there is this moduli stack that's relevant for the left-hand side. And two is that if you take seriously this idea of the function sheaf correspondence, the sheaves naturally live on this thing over the algebraic closure. So one goal that you can set is to refine the correspondence to kind of a statement in algebraic geometry. One thing I hope to do is formulate a precise version of a conjecture that's at least probably correct that involves kind of geometric objects. associated on both sides, and the problem is need a geometric object on the right hand side. So that will be the goal. Although let me emphasize that there's kind of an extra step here. As I said, that it's important if we pass the sheaves here, it's important to work over the algebraic closure of FQ. So on the right hand side, the thing that will be most primitive is parameterizing not arithmetic but étale representations of the étale fundamental group of X over the algebraic closure. So the kind of the categorical version of the geometrical equivalence correspondence will take place over the algebraic closure of a finite field. And then there will be some kind of abstract categorical procedure called traits of Frobenius that is meant to give an enhancement of the usual language. So that's the kind of setup for how the structure of this theory goes. Okay, so we want some kind of stack parameterizing representations of the étale fundamental group of a curve over the algebraic closure of a finite field. And so what's the problem? Well, let's consider the simpler case. So by analogy, consider X to be over the complex numbers. And so there are kind of two natural parameter spaces. Representations of the topological fundamental. Just going to call it I1 of X. So one is the kind of the most naive version of it, which actually will be the one most relevant here, is what's called the Betti version. So, well, we want to build some space whose points are representations of the fundamental group up to equivalence. The natural notion of equivalence is conjugation, of course. And, well, what do we do? Well, so say that, well, fundamental group is a finitely presented group. Let me not even worry about the fact that it's a curve. So it has some generators, some relations, and we can form, well, we can form the following space. Well, we want to study, we want to parameterize algebraic representations of this into some algebraic group. The structure of the kind of algebraic structure will come from the fact that G is the algebraic structure of G. Well, so what you can do is, well, what is a representation of such a thing? Well, for every generator, you need to name an element of G. So so you can look at the nth power of G. That's a nice affine algebraic variety. There's a map from this to G to the M, given by the relations, because the group structure is a regular map. There's a map of algebraic varieties. And then we can take the pre-image. We suppress X from the notation. So this will be, so we can take this fiber product, and if we are sophisticated, we can take this fiber product in the world of derived schemes.
Check the end.
What's that?
On the right.
Oh,
it's all G checks, right?
it's all, let me switch to G. Yeah. Yeah. Sorry.
It's local system for G.
It's local systems for sorry. Local systems for G. Yeah, thanks.
Where G is secretly G.
Well, G is secretly G checked. So these are so if you look at this paper, there are two different fonts for G. Because most of it is about this moduli space, and it's awkward to talk about G check without G being present most of the time, and so, anyway, there's a different font. I won't be able to use it on the Blackboard.
Other one, G-check.
Oh, no, that's.
Not allowed.
No, that
Double check is
can't
not.
do it. This B for Betti and box for frame.
Thank you.
Uh,
Frame because we haven't yet modded out by.
yeah, exactly. And so we define this Betti version of local systems. Betti. This is just this guy. Modulo conjugation. And you can take the stack function, of course. And the only caveat here is that, well, this is really only reasonable when there are two caveats. One, this is only reasonable when x is a k by 1. Like to get the correct derived structure. This is only reasonable when x is a k by 1. We'll fix that in a minute. I just wanted to give something very concrete. And also when this presentation is sort of a homotopy presentation. In other words, when the corresponding pushout in groups is the same as the corresponding is the equivalent to a corresponding pushout in simple. But anyway,
Would those?
when you have one relation, for instance, that's always the case.
Would that automatically be satisfied if the genus is sufficiently high or something like that?
I mean, this automatic, with the usual presentation of surface groups, this is satisfied. Okay, I mean, because it's one relation. There's no. That's not a problem. So I mean, in particular, if x is a surface of genus bigger than 0, and this is the usual presentation, this will give you kind of the correct derived stack. For the most, so the derived structure is important, but for most of the work will be kind of ignoring that.
So it will be the wrong derived stuff, even if you take like the fiber product to be in the derived sense or something.
But sometimes, yeah, I mean, for instance, suppose you just put in another relation, it's the same relation twice. It's the same presentation, but that it will change the derived structure. On the,
Oh.
exactly. So anyway, you have to, that's what I mean by it has to be a kind of a homotopy presentation. Again, not an issue for the usual presentation of surface. But anyway, yeah, so we have this nice parameter space, so great. So so why can't we do that? Well, okay, let me just say right away, the second version is what's called the deRham. So there's a kind of an alternate approach, a more abstract approach. Is the following. So take which will automatically gives a correct answer in all instances. So even when, for instance, when x has higher homotopy, it will kind of take those into account. The derived structure has to take those into account. So for instance, if x is P1, so the more abstract approach is to define it as a kind of a mapping stack. This is a mapping stack from kind of the constant, a constant free stack, which is just the underlying homotopy type of x into BG. Description of this for good circumstances. Just take one, and when it's presented this way, this is the same derived stack. So okay, great. So that's kind of one version. Flag this definition. One way to see that this is kind of the same thing is by taking some kind of cell decomposition, CW decomposition. Works for any. This is the kind of thing that works for any homotopy. So the second is the deRham version, which is kind of the more. So this is the parameter space. Of the bundles. X with a flat connection. So, let me give a more precise definition. In the spirit of this one, so the deRham version, this will take as our official definition. We can take the deRham stack of X and we can take the mapping stack from that BG.
I'm sorry, I do have a question of the earlier.
Yeah.
So I mean, BunG is literally if you just drop the underline of X, and just consider maps from X to BG. So
Yep.
how does like sort of forgetting some of the algebraic, so maybe it's like equivalent to forgetting the deBar structure or something like that, only remembering the homotopy type of the complex. Well, how does that give us? How do we see a G-torus over that gives us the same thing as a local system?
No. This doesn't, there's no map between X and this guy
Oh,
in general.
interesting. Okay.
This is just the kind of underlying homotopy type. This is the constant pre-stack, which assigns to any ring the homotopy type of X of C.
I see.
The one that's more relevant to your question is this one.
I see. Okay.
Which is the one that forgets down to G bundles. So this always has a map to BunG, just because you have a map from X to X deRham, and you pull back. And so in particular, the fact that you have this map more or less shows you that so like the point is there's the Riemann-Hilbert correspondence. Hilbert implies that the kind of E points, so E of C here. So yeah, there's going to be, it's helpful to have two notations for fields in this story. One lowercase k, that will be the field that like our curve type thing is defined over. So like in the main case of interest, it's going to be a finite field, and E is going to be the field of coefficients of our sheets. So in particular, this parameter space of Galois representations is supposed to be in this kind of setting over finite fields. The left-hand side, so BunG is a stack over FQ. On the other hand, this stack of Galois representations will be something over E, whatever our coefficient is. QO bar, yeah. Exactly. For the moment, though, let's take E to be C in this setting. So E points of the two things are the same. B and from G are the same. But this identification is very transcendental. It's not at all algebraic. Like these are very different as algebraic stacks. For instance, you can see that by taking X to be an elliptic curve and G to be equal to GL1. The Betti version just, is something that looks like this. And the deRham version is a torsor over the elliptic curve itself, because of this map, because it maps to pick 0, thickness, because it has a flat connection, necessarily maps to pick 0, and it's like a torsor for one forms on the elliptic curve, and in fact on the total space in the Hodge structure you can find the elliptic. So, in particular, like this guy knows about the elliptic curve, where that the Betti guy, of course, can't possibly distinguish different. Okay, so like the stacks are different. That's so that's kind of one subtlety in characteristic 0. So the usual formulation, the first formulation of the categorical geometric Langlands correspondence over the complex numbers involved this deRham version. There's also a Betti version, and I guess part of the goal of this project was to formulate a version that makes sense in more general contexts. Okay, so so that's what happens in this case. So what about x over q bar? So the problem is this. So let's take the first approach. I don't want to say anything about the deRham version in that setting. You can try to imagine some crystalline version, and that's even more complicated than the Étale version. So, but we can try to study representations the Étale fundamental group of X into G into G over now Q. Now this will take place over Q bar. Now our group is over Q bar. That's the natural sort of coefficients to consider. So what's the problem? The problem is that this now, so this is not a discrete group anymore. This has a topology. So this is a profinite. This is some profinite group. And what we're interested in is not all representations, just as groups, but we're interested. So G of Q bar has a topology coming from the topology of Q bar, and we're interested in continuous representations. Now I can explain kind of the first no-go result in this business. Now we have a problem. So let me illustrate the problem. We want some parameter space. And it's defined, and it's supposed to be some kind of a stack or some kind of a has some kind of algebraic structure over our field, which is Q bar. But the point is, the kind of continuous representations don't seem to fit in this framework. So consider an example, e.g., so consider representations. So let's take the simplest possible profinite group, which is z hat, and G to be GM. So let's study representations like this. So if we wanted if there was a parameter space, so clearly, so what would we want out of a parameter space? Would want, or no, let me call it rep of C hat. Well, at the very least, well, these are all these should be. Certainly, this should sit inside representations of just Z. Of course, this is determined. Each such representation is determined by where the topological generator goes. So this is just GM times BGM. This is just follow that construction. But the problem is, but if you evaluate it on our field, so the closed points, the Q bar points, what should they be? Well, the point is such a representation. So a representation is the same as so these are the same as maps from Z into ZL bar. So the QL bar points of this should be ZL bar cross. And so there's like the, which is not anyway, kind of sitting inside somehow where GM, I'm ignoring this part because this doesn't have any QL bar of QL bar, which is QL bar cross. And of course, there's no stack or scheme of finite type that does this. This is just impossible. there's no way to, seemingly, there's no way to produce something reasonable that will do this. So this is sort of where things stood before this, where this was kind of the main, this kind of thing was the main obstruction to trying to build a reasonable parameter space of local systems. Okay.
What is the problem?
Well, the problem is, I mean, try to imagine like a finite type scheme over QL bar is defined over QL bar, and you want it to be somehow mapping to GM in a reasonable way, so that QL bar points of it would be in bijection with ZL bar of X. This is problematic.
Sort of defined by an inequality.
It's sort of defined, exactly. It's defined by an inequality rather than an equality. So, but anyway, I mean, it's easy to see that, for instance, that there can't be any finite type scheme that does this over QL bar.
Maybe this is a relevant question, but in the very classical Langlands correspondences, usually the representation theory side is defined over C, but you have that extra data of these Veil-Leiden representations of that unipotent element. Is that, when you're dealing over QL bar, that goes away, is my impression, right? Is that correct, or?
Sorry, in this setting, we're over in the geometric sense. So
Sure,
what we want to be studying is Veil representation. And that will come from the passage from the algebraic closure to the original curve. So what we'll want to study is not this thing, Taiwan arithmetic, which is the big group.
Right, yeah.
And so that will sort of come for free from once we understand the situation for the algebraic. So somehow part of the idea is to try to break up what we're trying to achieve here with the Langlands correspondence into two parts, into a kind of a geometric statement and an arithmetic statement. The geometric statement will be taking place over the algebraic closure, and then there will be some procedure to it will be kind of a higher categorical statement, and then there will be some procedure to extract an arithmetic statement. And that will have to do with exactly looking at the representations of the Veil group. Okay, so nevertheless, well, so what to do? Well, we can try to forge ahead anyway. Well, I mean, this thing tells us that if we want any kind of parameter space, it can't be as nice as we can possibly hope. Like, it can't be some stack of finite time. This is impossible. That's what this example shows. But nevertheless, we can try to generalize what kind of parameter spaces we allow. And this will turn out to be true. So the idea is to apply. So you can try to implement several ideas. One can really try to make sense of this moduli of continuous representations in some way. That's a reasonable idea, and it will, I think, lead to essentially the same space as I'm about to describe. But there's a kind of a more categorical approach that doesn't worry so much about the topology, which is to apply the Tanakian form. So what I mean by this is that, let me remind you. I mean, so suppose X, let me just do this in the greatest amount of generality, is some pre-stack. Then there's an equivalence between G bundles on X, well, which of course is the same thing as maps from X to BG. That's the definition of what this is. Well, there's a description of it in terms of the representations of G. So this is the same as, well, write the exact tensor functors from representations of G to quasi-coherent G's on X. So if you're not comfortable with X being a pre-stack, so I guess the usual thing is for like X a scheme, but by definition, a G bundle on a pre-stack is a compatible system of G bundles on every scheme mapping to it. So this immediately reduces to that case. And so what's the, let me try to, I think, what's that? No conditions on X is any. I mean, again, because a G bundle on X is the same thing as a G bundle on every scheme mapping to X, and I can just compose with a restriction functor. And this is by definition the inverse limit. Importantly, the way the right T exact works is also like the connective things here are the inverse limit of connective things, of modules over affine scheme mapping to X. So I guess this was mentioned before in some earlier instance, at least in some earlier instance of this seminar. So
You probably mentioned it.
Yeah.
So top one.
yeah, I think so. So yeah, I mean, let me emphasize, I said right T exact, so all categories are derived. Probably the ongoing convention here, I hope.
Yeah, begrudgingly, we came around, right? We could have saved some misery by not being so begrudging, but.
So let me reformulate. So now let me use this point of view to reformulate these two approaches in the setting of Riemann surfaces, algebraic curves over the complex numbers. Reformulation, lock in. Formulation. So first, let's start with the Betti one. So this is going to be isomorphic to, well, let me say it like this. S point, S is some test affine scheme. This is going to be, well, by definition, I said this was maps. This was that mapping stack right there. So I take this homotopy type X of C, I multiply that by S, and map that to BG. Right, that's the definition of the maps underline stack by definition. And now I can apply, this is why I wanted this pre-stack to be arbitrary. So I can apply it to things like this. This is the same as right T exact. Things are functors from their representations of G. But I notice that that's quasi-coherent sheaves on BG. Two quasi-coherent sheaves on this guy. Now, well, so this is the quasi-coherent sheaves on anything times an affine scheme is the tensor product of quasi-coherent sheaves on that thing, tensor quasi-coherent sheaves on that affine scheme. And well, let's see. What is quasi-coherent sheaves on the constant pre-stack given by some homotopy type? So you take a pre-stack, which is like given by a homotopy type. To every test affine scheme, it assigns that homotopy type. What is quasi-coherent sheaves? It's not vect because it's a vector space for every point. For every so everything factors through point, certainly. So every map factors through point. So you only have to care about when your test scheme is a point. But then there's a space. So but how does this work? For every point, for for every k point, for every e point, you're supposed to get an e vector space. In other words, for every point of x of c, you're supposed to get a vector space, and this is a kind of, we're thinking of this as a homotopy type. So for every, it's like an infinity groupoid, for every morphism, for every path, we're supposed to get a map of vector spaces.
It's like the K theory.
And so on.
Sorry, in my for understanding, so you are thinking about local system, then why is the target of this representation G to quasi-coherent? If you replace this quasi-coherent by local system of x t times this, then it is, but it's not okay. But you like to put you are putting category of quasi-coherent sheaves there.
Yeah,
And what happens if you put the category local system? But
so let me say, first of all, the S, it will be kind of coherent in the S direction. And quasi-coherent sheaves on this is, let me write it like this. This is sheaves on the homotopy type, which are locally constant. So I want to distinguish, I want to avoid the word local systems because I'm allowing infinite rank. And this is very important because when I'm tensoring this, that's the same thing as like if S is spec R, this is the same thing as locally constant sheaves of R modules. And if R is infinite dimensional, this is a meaningful,
Thank you.
yeah. So this is what that is. By the way, another way of saying what this is, for those more. Think of this infinity groupoid as a homotopy type as an infinity groupoid. This is functors of infinity categories from this infinity groupoid. That's, but I mean, also this has a more classical description as the full subcategory of the unbounded derived category of sheaves on this topological vector space, such that all the homology sheaves are locally constant. Do either of them. But the point is, so that's one. And the second thing, similarly, this, again, times S. Put it in the other order. It doesn't matter. So this is the same thing. Same kind of functors from ref G into D modules on X. So quasi-coherent sheaves on the deRham stack, as we know, are D modules. And X is the derived category of D modules. And so okay, yeah. So this, so one thing I want to emphasize is that this, hopefully, this makes these two stacks look a little bit more uniform. What this suggests is that the key input is not some kind of a space, but what is the kind of the version of what our notion of local systems is. So the key input is the category of locally constant sheaves. So long as we have some tensor category, we can plug that into this formula. I guess it has to have a T structure. It has to have a T structure in order for it makes sense to talk about right T exact functors. But that's it. That's all we need. Makes sense.
So in the one case, it comes from just the homotopy type of X.
Yeah, in one case, it comes from the homotopy type, in the other case, it's algebraic demon.
Flat nation.
Yeah. Uh, and so now, so the idea is to bravely and boldly plug in what we have in the Étale set. Have just give it a name. We call quasi-lease. This is the full subcategory of all Étale sheaves. So I don't know, l-adic. I don't know how well it means l-adic sheaves on X, consisting of complexes with in local system homology sheaves. So hopefully, as people have been indoctrinated in the seminar, it's usually better to consider large categories rather than small ones. So by this, I probably mean end of the usual thing that you might consider. So you can consider
Pro-Étale.
no,
No, they make the opposite.
oh, no, no,
In-
not, it's just int constructible, yeah, so this is int of constructible. Constructible at all. This is what I mean. So the standard one is just constructible l-adic sheaves, and I just want to take int of that. As to large categories, there's an actual subcategory of that where all the homology sheaves are in lease. In other words, in local systems.
Sorry, but if you go back to so is this gonna embed inside sheaves on the protocol side, like QL?
Yeah.
For the large sheaves?
Yeah, certainly. Yeah, this guy, yeah. I mean, because this guy, yes. Yeah, so this I think this is a full sub, like in the Chilton. Full subcategory.
And you can characterize it in the same way that the objects from the protocol sites, individual homology sheaves are like.
Oh, yeah, I believe so. I believe so, yeah. Okay, great. So we have this thing, and now we define a stack of local systems with restricted variation. Yes. Just by the same formula. Right. Oh, we just apply the same, definition. Okay, so what does this give? I want to partly, so one of the goals of this talk is explain this word restricted variation. What is being restricted?
The main problem for what do we do with that problem? Like,
Oh, it's built into this category. So remember this category. So for instance, the heart, so this category has a T structure. So in almost all cases of interest. So it turns out that when X is a curve that's not T1, this category is the derived category of its heart. It's kind of it turns out to be a very important technical point for this work. And in all cases, the heart of this thing is just continuous finite dimensional representations of the étale fundamental,
Which is very small in the case of P1.
which is very small in case of P1, yes.
Yeah, I know, so it's derived technically. See why it will fail for P1 at least.
Yeah, so it's obviously not true for P1. For other things, it's not.
P1's much smaller, but is there a definition without the restriction, like can you define block system that it's all same?
No, this is all you get. I mean, partly because of that issue. So there's no. So no. I mean, not as an algebraic stack. I mean, you can try to imagine some kind of analytic stack, which would do better, but I don't know, that would run counter to the what the original motivation of trying to apply algebraic geometry situation.
So the clarify, so it's so that's something, okay, so that's not P1, that it's something that you can build, that you build or that it's sort of built from the classical category of l-adic systems on doing category l-adic.
Yeah, so in general, so you can look at, before you take int, you can take the least, so in other words, complexes where in the constructible world where all the homology sheaves are local systems. And you can take int of that. And in all cases except P1, that will agree with this. What is true in general for any X is that this is the left completion. This guy is always left. Anyway,
Wait, what happens with P1, sorry.
I mean, it's trivial.
well, no, there are two subtleties about Pi1. One is that this obviously can't be the direct category of its heart because Pi1 is trivial. There's a separate issue, which is that you can look at end of kind of perfect local systems on P1, which is also not the derived category of its heart, but it's also not this. In that case, it turns out that this thing is the left completion. And this thing actually is all local systems on the two-sphere, it turns out. Anyway, I don't. It's probably too fine a point to dwell on for this kind of talk. Minutes. So let me try to do so note that we can also consider Betti and deRham versions of this restricted version. So I just have to name what this quasi-least thing means. There are two versions. So the natural thing inside I can take this to be same condition, complexes. This homology is given by in finite dimensional representations. So it's just all locally constant sheaves such that every homology group, well, those are representations of the topological fundamental group. And I ask that it be a union of finite dimensional representations. That's the analog. Of course, if over C, if I take this is going to be the same as this category for a variety over C. comparison results. So that's one version. And another version.
So the way you're saying it there, it's for X being like a K factor or something.
No. And it's a condition on the homology. Complexes.
Oh, I see, because in the hard is gonna be representations.
The hard is always representations of Galois, yeah. Yeah. X, this is kind of in of regular polynomial. So you can, the analogous finiteness restrictions for D modules is asking for it to be a regular polynomial. And I don't know, maybe let me put subscripts. So for X over C, all three versions of these quasi-Lees are actually identical. These, that's the Attell one, is isomorphic. Betti one. So that's a version of the usual comparison with Attell cohomology over the complex numbers. And this is the Riemann-Hilbert response.
Is there something, one figure that you had, got like multiple systems?
Sorry, here?
Yeah.
This is LC means locally constant.
Sorry, the second one, the.
Yeah, let me say it like this. You're right. Monomic local systems. Yeah, sorry. To get the inequivalence of categories, I need that. If I plug this in, it actually doesn't matter. It would be the same. So, I mean, this would be false, but the corresponding moduli spaces would be the same. Yeah, thanks.
And who's Riemann-Hilbert? Is this one?
I mean, I don't know, the one, the disputed one. That identifies the derived category of regular holonomic D modules with constructible sheaves.
I see. Okay.
With a constructible derived category. I don't know, Kashiwara, Kawai, Saito.
But again, it's kind of the least case, right? So it's even.
It's still least case, yeah. So this is easier. Okay. This. Some examples. So one kind of interesting upshot is that in this kind of, whatever this word restricted means, all the versions of this moduli space agree over the complex numbers. So that's the good news. But now for the bad news, which is that these things are, this is a pretty unreasonable thing to do, to restrict to infinite dimension. The reason is because what I already mentioned here, like in this Betti setting, let's compare. Like if you like spec R point, an R point is an R module of local systems. And if R, so you know, like the trivial one is an example that you might want to take. That's like the most basic one. And the trivial one is not the best example, but the point is this condition that as a representation, it's infinite dimensional is a very stringent when the algebra of parameters is infinite dimensional. So this is why, like, if for finite dimensional algebras, this will make no difference. Like for on Artinian points, all of these things will be the same. But for rings that are infinite dimensional over the base field, these will look pretty different. So let me try to illustrate that. Example, we'll do this example, and then we'll take a break. is to take, let me work in the Betti setting. So take X to be a circle. So we can study this restricted or GM of X. So let's study this restricted version of so what is it? So spec R. And let's assume, so take R to be a classical ring, so there's nothing derived happening. R is an ordinary ring, which is, just for simplicity, let's say irreducible. Reduced and irreducible. You can weaken that. If, for instance, connected. But well, what we want, well, let's apply the definition. So this is functors from representations. GM. That's functors. And in fact, because R is not derived, I can stick to the abelian categories. There's no problem. So it's tensor functors from here into what? So in finite dimensional Z modules. I1 reps tensor R mod. Right? So what is this? This is the same as a line bundle on spec R together with an automorphism such that L. So that would be just, if I didn't do infinite dimensional, that would be just all such things. That would be the same as a without this condition. That would be just all line bundles on spec R together with an automorph. That's what would be a spec R point of just not restricted, but Betti version of this circle. But now we're imposing the condition that L is a direct sum of generalized eigenspaces for L. This is the condition of being in landing in infinite dimension. And in particular, this condition implies, under the condition that R is reduced and irreducible, implies that the line bundle has to be trivial, because this decomposition has to be compatible with the R module structure. So, projective module of rank 1, and that so L is the trivial R module, and alpha is just by multiplication by some element of the ground. R times alpha R, where alpha is an element of E. This is what up to the natural notion of equivalence. Here. And so the upshot, does that make sense? And so the upshot is that the stack splits up as an infinite direct sum over all possible points of E into copies of, well, BGL. That's the natural notion of equivalence. So the upshot of this kind of a slight enhancement of the calculation I just did So it looks like, so from this point of view, it looks like we haven't really achieved very much. We wanted to parameterize like one-dimensional local systems, and we say, okay, no problem. We'll build an algebraic parameter space where there's one connected component for every point that we're interested in. So that's sort of the bad news. But we'll see that this is sort of as bad as it gets, and that in general, it's something kind of in between the two extremes, and will give us useful information. Yeah.
This is only true at the reduced level, right?
Oh, yeah.
Because you'll
Yes,
have
yeah.
deformations.
Yeah. This is only true at the reduced.
Wait, what's it like for the non-reduced?
What's that?
What's it like without the reduced?
Oh,
Uniform completion.
yeah. And let me say, I'll say it carefully after the break.
Okay.
Yeah, thanks for pointing that out. Indeed it is. Indeed it's at the reduced level, yeah. So anyway, so I wanted to end with the bad news, but there will be good news after the break. Yeah, I'm back. All right. So that was the bad news, is that at least on the reduced level, this thing looks like just a bunch of copies of BGM. So you know, you do this kind of calculation and it's a little bit discouraging. It looks like you've gone through some kind of abstract formalism and didn't really get any. But that's not really true. So there are two bits of good news here. Another thing, rather than restricting ourselves to reductive groups, let's look at the other extreme example of unipotent groups. For simplicity, so let's consider the additive group. Another example is equal to DNA rather than multiplicative group. So I'll say it later what the general thing for the multiplicative group looks like, or in fact for any group. But let's consider the case of the additive. So in this case, the situation is much better. So the point is, there's an identification. So algebraic representations of GA, well, there are different ways of thinking about it. Like in terms of kind of basic linear algebra, there are Jordan blocks with generalized eigenvalue 1. But you can identify this with your duality. This is the same thing as modules for an algebra. C, where C has homological degree 1. It's a commutative differential graded algebra, and this is a tensor equivalence. I guess this is a good time to emphasize that the field E, unlike the field K, is always characteristic 0. Oh, whoops. No, very false outside of characteristics.
So the always talking about non-finite dimensional representations.
Here,
In all representations.
this is all representations. But all representations of an algebraic group are essentially, by definition, indefinite dimension. So because representations of an algebraic group are comodules of corresponding algebra, which are indefinite dimension.
Do these functors also be continuous?
What's that? Yeah, functors are co-limit preserving.
Co-limit.
Yeah, that's we live in that world always. That's part of the deal of working with big categories here. All functors that we'll ever consider are going to be co-limit preserving. But yeah, thanks for this. So the point is, so the upshot. So because of this, what this implies is that tensor functors from GA into some symmetric monoidal categories, all tensor functors. This is the same as maps commutative algebras from this ring into endomorphisms of the unit. That's it's a kind of an affine situation. It behaves like a it's clear. And so, well, this is great. Because, well, let's apply it to. So let's apply it to. So now let's consider restricted local systems. Okay. X. This by definition is tensor functors. From okay into quasi-lease of X tensor choose on X. So importantly, the unit here is connective, and that guarantees that all such tensor functors are right TXF. This is why that's the relationship to the T structure. Relevant fact is that in this category, the unit is connected. So I can just say all tensor. And so, well, this is the same as maps of algebras of endomorphisms of the unit here is what? Well, endomorphisms of the unit here, tensor endomorphisms of the unit here. So that's the same thing as one way or another, the homology of X with coefficients in R. S spec R. Whatever setting we're in, deRham, Betti, or et al., it's this kind of thing. Actually, let me say it. Yes, I really need E tensor R. Clarify it. And maybe in the et al. Setting, it's not otherwise clear what I mean by this. So it's maps like this, and this is. Importantly, what's that?
Do that to preserve grading? Or just in?
No. It's sorry. I mean, what kind of maps? This is maps. So you write it in a way that what am I doing? Let me emphasize that it's cochains. First of all, and both of these are commutative differential graded elements. It's maps of commutative differential graded elements. Yeah. But the point is, well, what is such a thing? Well, this is just the same thing. This is just the space in del-con applied to so a map of CTJs like this just is determined. Xi is a free generator, so it's just determined by where Xi goes. So I just take this guy, E tensor R. I shift it by 1, and I take kind of the total space. Well, I don't count this chamber. So in particular, notice that this is a connected. This is something connected. And in particular, so the upshot, and moreover, it didn't care about the difference between quasi-lease and other versions. All it cared about, all it wanted out of this quasi-lease category is endomorphisms of the unit. And pretty much in all the versions, wherever they make sense, endomorphism of the unit is the same. Is that like in so over C, we have this guy restricted of X. This is equivalent to the other two. Betti well, I'm supposed to assign a space. Oh, okay. It's the space of map. It's the space of algebra maps, which is the space of maps of chain complexes from just this guy, the generator, because that's a free CDJ into that, and that's how mapping spaces in chain complexes. I take a mapping chain complex and I plane dot conjugate in a space. So
Can you explain one more time why you disagree?
I mean, same calculation, just replace quasi-least by any of the other ones. And endomorphism, the relevant fact was that the unit was compact. And that endomorphism of the unit is cochains on the space. That was the relevance thing. So like it's a kind of a derived version of the total space of a vector space, is what this is. Okay.
So you're saying the point is if I replace Q least by any of these other
Yeah.
versions, it's the same calculation.
Exactly.
Yeah, because the unit is the same.
The unit is the same, and yeah. Nice. And well, in order, well, it's important that the unit is compact also. Because I'm using something about how endomorphisms and tensor product of calibration. A little bit of subtlety, but no problem. So the point is, like for GA and similarly for unipotent groups, these things are the same. So the way things were bad is because GM, is because GM was reductive. And so that's one bit of good news, is at least, of course we care about reductive groups, general reductive groups. But so the other bit of good news second bit of good news, which is, well, that calculation before was, as Justin rightly pointed out, was about the reduced part of the thing. But the other bit of good news is that the tangent spaces at points are actually correct, actually agreed for all three. For all three versions of the moduli spaces. Second bit of news. Is that given an E point maybe so given a point, now I don't have to write any subscript G. So, because the E points are the same for all three things. Almost tautologically. Then what we have is I don't know, the cotangent complex. E is, well, we can write down what this is in all three versions. It's cochains It's this thing in all three versions. Let me try to explain this formula for a second. So this is, this is if you have a, one way or another, if you have a principal G bundle, you can form the associate on, or like a G local system, you can form the associated local system corresponding to the Lie algebra. You can take the kind of importantly, this will be, the observation is that this will be in this will just be Lie's. So this lies in whatever the smallest subcategory that you might want. You can take homology of X with coefficients on this local system in any of the versions. Those are all the same. That's hom from the unit, which lies in all of them, to this one shifted by one, and take the dual. This is the no, not the Lie algebra, just homology of this local system. So it will be the same in all three versions. I guess maybe it's easiest to compute. I don't know, in either the deRham or Betti. So the reason it's the same, let me try to wave my hand about why it's the same in all three versions. Yeah.
What is that symbol? Boldface L.
L? Oh, this is cotangent complex. Yeah, I shouldn't have done that. In this business, the standard notation for cotangent complex is boldface L. In this business, for good reason, one tries to avoid this boldface L because that usually stands for the Langland's dual function, Langland's duality function.
Sorry, this is really annoying, but then do you want to dualize the homology, not the cohomology?
See, no, I think I said it. I think I said it the way I put it.
We're asking the star to be the top or the bottom.
Yeah, I think.
X is projective. It's
Well, no, I mean, up to there's some shifts.
Would become.
no, but I mean, I'm just saying like lower Schrieffer, lower star. Proper scheme is the same, right? So
Yeah, it's a dualizing complex involves a shift. So homology is right.
either way you're applying, it's definitely something.
Anyway,
Sorry. It's yeah.
I-
that's different.
Anyway, yeah, I mean, so it's easiest to like, there's a general for, so why is this true? Let me just, so first of all, before giving the formula, let me try to wave my hands about why it's the same for all three versions, is because in this case, like the way you compute the cotangent complex is you plug in S to be local Artinian rings, and those are finite dimensional. And so for when the ring is finite dimensional, the functors always land in the smaller category. There's no restriction. And so for local Artinian rings, the points are for the same reason that the E points are all the same. The points with values in the local Artinian ring are the same, and so that automatically implies that the cotangent complex has to be the same. And this, I don't know, maybe the easiest is in one of the other cases to compute. There's a general formula for the cotangent complex of a mapping stack. And if you apply that, you get this, using the fact that the dual of this guy is with a shift is the cotangent complex of DG. I think I also talked about a while back here. So sort of the good news is that the kind of the deformation theory infinitesimally, the points look the same in all three versions. So we've successfully captured the infinitesimal information. We've successfully captured, even in this gym example, the automorphisms. In the case that there's some unipotents, then we've captured how all of those vary. So the idea of upshot.
So the only problem is that all of the points are disconnected from one another in the one example.
Yeah, that's right. So the
Reduction
option,
example.
yeah. So the upshot is, well, we have natural functors. So let me just restrict it over C, because over in the l-adic world, there's kind of nothing to compare to. So over C, we have maps, kind of inclusions, tree stacks. Betti. And so this one restricted version, which is the same as the restricted Betti, as we said, and the restricted deRham, maps to both of them. So see, essentially, because for a tensor functor to land in here, that's a full subcategory of the thing where I take a larger version and an enlargement of this. And so it's as a result, it's a subfunctor. Or I'm saying is that it's a subfunctor. It's for every S, it's a condition. It's a subspace of things to land in the smaller version. And which are formally at all. So formally at all means it's an isomorphism on cotangent. Right. So I guess I should have said from this example, this word restricted variation, it means that we're breaking up something that you know, like whenever you have a kind of a larger Betti or deRham moduli space, those are always connected. And so we're breaking that up into possibly many connected components by limiting how families of local systems can vary. Yeah. Yeah. Oh, times BGM, yes. Exactly, yes, that's exactly what it is, precise. All right, so now you're probably so these are formally at all. So in fact, yeah, so now you're probably wondering what they look like in general. So I did this example of GA, everything was great. It's as good as we could hope for. I did this example with GM, and that looked terrible. So what is it in general? So right. Well, for something. So let's study. So let's compare with the Betti case. That's maybe the most intuitive way of saying what this is. So what does general? So the easiest way to answer the question is when we're working over the complex numbers, when we have the Betti version of the stack to compare to, is that first of all, let me say there's a theorem of Richardson from the 80s, which says the following: is that it's purely about the Betti version, nothing to do with the restricted version. Is that you look at Galois Betti. So I guess this theorem of Richardson was really the starting point for von Simplifors.
This is exactly the insights and
Yeah.
use to show.
Yeah, that's right.
This
It's an
gives-
affine. Moduli space. So, and so in general, this is it's derived. So with, this isn't how Richardson stated it.
Certainly not.
But the first statement is that H0 of this thing, this is in general derived. Say, this is these excursion operators. And the second thing is that maximal ideals closed points of S are in bijection with representations from pi1 of x to G with equivalent semi-simplifications. So, I don't know. I know there was some discussion of excursion operators before. Were there any discussion of what semi-simple representations mean in this context for a general group and what is
The image lies in the Levi. So
Yeah.
That is not, oh, yes. Hopefully everyone is paying attention.
I think. So the point is that for any, there's a notion of such a thing, being semi-simple. So first of all, there's a notion of a representation being irreducible. Irreducible means the following. Irreducible means that the image doesn't lie in any proper parameters. So irreducible means, and you can think if you use GLN, this exactly corresponds to the usual notion of irreducible, because if you had a sub-representation, you'd fix a flat. And semi-simple means the following, that if you can factor through some parabolic, then it actually comes induced from the corresponding Betti. And for any representation, there's a kind of a minimal parabolic that it factors through, and then you can kind of take the corresponding, and then you can take the corresponding representation of the Levy and reduce it up to representation of D, and that's a semi-simplification, and that's its semi-simplification. So like the connected components are exactly like like the semi-simple types of representations. This is what in general indexes connected components. Well, we'll see that this is what indexes points of this space, and we'll see that that's exactly the same as what indexes connected components of this restricted space.
So in the Richardson theorem, there was this arbitrarily large powers, G times G times G times G arbitrarily many times, but for a given X, this would only require the number of times that is sort of, I don't know, the genus, the number of generators of pi.
Oh, you're asking about like how excursion operators work?
Yeah, so like in the
Like
general case.
how many legs your Stukas have? or something?
Yeah, like, the heck of, yeah,
No, I think you want
arbitrary.
You
legs.
want arbitrary.
But
At least if you want the whole thing without H.
I see. But in our definition of loxis B, right, there were only as many as there were R's, right?
No, that's not where those come from.
Ah, okay. Makes sense.
Those are different. Those don't quite correspond.
Misdirected by saying
Yeah.
G times G times G.
No, those are doing different things. Those are doing different things. Yeah, there's a kind of a derived version explain of this fact. Where explained in this 4-author paper, which is the precursor to the 6-author paper. GKRV, yeah.
Notably, R is in both small set and large.
What's that?
R is in both the small set and.
Well, one of the R's. Yeah, and so we have this map, this Betti local systems mapping to the force moduli space, and the theorem is that Lux is restricted whenever you have this Betti one to compare to. This is the disjoint union over closed points of, you take the preimage, this closed point. Let me write it like this. So the formal completion at the closed substack, which is the preimage of this point. So this is this is kind of the most geometric way I know how to say what the space looks like. So in particular, you're grouping together all local systems that have the same semi-simplification, which should so somehow, what was the difference between GM and GA? Well, in GM, everything was semi-simple, so all of them are you couldn't go from one to the other by studying kind of extensions. In the case of GA, well, everything is built. Every GA local system is built as a sequence of extensions of the trivium. And so you're sort of gluing together. It's not that you're separating all the points, you're gluing together the ones that you can build out of extensions. The same kind of the same composition factors. Okay, so this is one answer to what this is. What's that?
What are the reduced points?
Oh, well, the reduced points are, well, it's a little complicated to say. I mean, it's the reduced point, it's these preimages, or the reduced part of this preimage. You know, that could be, if for an irreducible local system, that will be 1. So like you're asking, like, what gets collapsed here? Well, I mean, if two, I mean, I don't know. The reduced points are all representations, right? I mean, you're asking, and they're grouped into connected components according to their semi-simplification. So anyway, so that's in particular an answer to what you can plug in GM in a circle, and that's the answer in that case. So in general, that's one answer. This, yes. So in general, and what do I mean by in general? Is that, well, suppose this was in the situation where I had something to compare to. What about if I don't? What about the l-adic settings? e.g. l-adic setting. We prove is the following. This is the disjoint union over. Right.
There's no way of gluing those fibers together. So it's not disjoint, they're not glued along the base.
Oh,
Because the base you said is affine scheme, right?
I mean-
Richardson theorem.
there is, you can have the Betti moduli space. If you want to glue them together, you can glue them to the Betti moduli space. But the point, and that's okay, in the situation where that makes sense, but like if we want to do this in the l-adic setting, there is no. Like this S doesn't exist, and this Betti moduli space. I told you in terms of the comparison to. In terms of the comparison to this thing.
So yeah, in the Betti space case, S has a nice interpretation of the affine scheme. But
Yeah, that's
but
right.
Not in the l-adic.
That's right, exactly. And in the l-adic, there's really nothing more you can do. This is kind of the best that seems available from several points of view. And also, as I'll try to explain, this gives you exactly what you want. So the fact that this looks like you're splitting up into infinitely many components is actually going to be a feature in many, as I will try to explain. So let me just say, okay, let me say this a little bit imprecisely. P parabolic. B sigma reducible represent. Irreducible representation into P. Oops. Into M, the Levy quotient. So this is like by some simplification. And there's some equivalence relation on these that I don't want to describe. So for each one of these, there's a component. There's a component. Sigma. And each component is an and affine formal scheme quotiented out by G. This is the kind of thing that this is what this looks like. No. So it's like so this just means a formal completion of an affine scheme inside another affine scheme. So it's better than an ind affine in scheme, for instance. Like the reduced part is just an affine scheme, and you're quotienting out by G. So it's not an algebraic stack, but it's not so far from being an algebraic stack. It's like it has infinitely many connected components. Well, okay. C'est la vie. And each one almost looks like an affine scheme modulo your group, but it's some formal completion of one affine in another. So this is the structure of this. So it's as I said initially, you can't hope for it to be like a stack or anything like a finite type or anything like that from the simple example. But this is what it ends up being.
In the general setting, you can make sense of success without the restriction. You have a similar,
No, there's no, I mean, that's the only thing you have. I mean, that's sort of the point. Is that like in the case of l-adic sheaves, there's no other version. There's no other space parameterizing.
sorry, like in the deRham.
Yeah, so in the, oh, sorry, what are you asking then? Sorry.
Do you have a similar decomposition in like the deRham setting?
No, all of these are connected. In the other setting, like in the deRham setting, it's connected, in the Betti setting, it's connected. These are connected stacks, whereas,
Yeah, and can you say a few words for like why that's the indexing set?
well, hopefully it's a little, hopefully it's believable that these correspond to semi-simplifications. So a semi-simple one is like you pick a parabolic, that's like the length of the flag or something. And then picking an irreducible representation of Levy is just picking the irreducible pieces. It's picking the piece of the semi-simplification. Anyway, I mean, it's more subtle than that. And for instance, there's a kind of an equivalence relation on that. Like these don't all give different things.
When we think of the language parameters, mapping. The image doesn't need to be very large, does it? Just sort of the question is whether it's. I mean, it can be finite image, like the.
Well, anyway, so this is the proposal, I think, for the moduli space, not of Langland's parameters. Because the Langland's parameters have to do with arithmetic. This is kind of the geometric version.
I see.
So it turns out that the Langland's parameters is bigger. Actually, so let me state. So I have to use the last few minutes to get back to what this does for the Langland's program. So the conjecture. So now one can use this moduli space to formulate a kind of a categorical version of the Langland's conjecture for curves over finite fields. So conjecture of X is a curve over bar. Now this is formulated over the algebraic closure, which is that you look at the moduli. You look at the moduli stack of G bundles. Importantly, this is a stack over FQ bar. But you look at l-adic sheaves on it, so the coefficients are QL with nilpotent singular support in the sense that Sasha explained. That's on the left-hand side, and here, well, it's something like quasi-coherent sheaves on this thing. Well, with some slight modification. I want a bit of a warning. There's kind of nil on both sides. It looks symmetric, but that's misleading. One shouldn't. They're different nils, and they're playing different roles, and they're doing different things. So the point is, this is the conjecture that we're able to formulate as a result of all this work. And well, I don't know. Let me briefly tell you. Let me briefly say what evidence there is for that conjecture. I guess it's now a theorem for GLM. But even before that, we prove that there's an action. Whatever this thing is, it's some enlarged version of quasi-coherent sheaves. But certainly this guy, kind of tautologically, quasi-coherent sheaves acts on this category. And so that there's a natural action on this side. By the way, already this has a surprising consequence because this guy is a disjoint union of lots of connected components that tells you that even though this is a connected stack, this category splits as a direct sum of categories. But just because you have this action, you can apply the projectors to each of the connected components here. So this tells you is that there's a kind of spectral, categorical spectral decomposition. Whatever is indexing the connected components here. So that's kind of a very weird statement, is that just imposing the nilpotent singular support condition breaks up this category into infinite many pieces. So that's kind of one nice thing. Another thing is that, so if x is defined over actually the finite field, well, then there's an action then get just by transfer of structure, even though everything is in characteristic 0, on this moduli space, there's an action of Frobenius. So we define. Now this is the moduli space of Langland's parameters, which is the fixed points of this action. Meta. The derived fixed points, this thing. So this is a very derived, now this is very derived. We took something like mildly derived and took fixed points of some automorphism. That makes it really derived. Truly so. And so, there's some more good news. The more good news is that this turns out, even though it's built from this kind of somewhat weird object with infinitely many connected components, each one looks like a formal completion of something. All of that goes away once you take the fixed points of Frobenius. Is that this guy is a quasi-compact stack stack finite. All of that bad stuff went away, right? Just by taking fixed points of Frobenius. Finally, a formal consequence of the conjecture gives a kind of a more precise formulation of the Langland's force, which is what I started with. We wanted to kind of relate automorphic forms and Galois representations, or Langland's parameters. So now we have a space of Langland's parameters, and a corollary is that, well, plus other stuff. Plus space vector. It's called the conjecture in that paper, but it's a theorem. I don't want to be misleading about it.
Was it a theorem by the time the paper was written, or was it?
Well, I don't know. The paper went through some, I mean, it was proved shortly after, but it was genuinely proved. It's formulated as a conjecture in the paper, there's a later paper, slightly later paper, which proves this conjecture. At the time this paper was being written, this truly was a conjecture. It's not. Is that this guy has this description. You naively might guess is that its functions on the space of Langlands parameters would give you automorphic. But that is not true. What this predicts is that on the space of Langlands parameters, it's the dual length. Because this is very singular. And so these are very different functions. Exactly like the need for orthoparameters in this business is exactly measured, it's somehow exactly geometrically measured by the singularities of this moduli space of Langlands parameters. I should stop here. Very much.
Any questions? There is a big conjecture, the glass conjecture. There is a corollary which you prove independently of the big conjecture.
No, it's well, assuming the big conjecture, it's corollary to the conjecture.
Ah, okay. You don't have a.
Restricted geometric ones.
Sorry, but how did you, didn't you, the second paper, didn't you do it in the second paper even though the advance wasn't proven?
No, the second, sorry. The paper proved something about the trace of this trace.
Trace.
There was this kind of trace
Yeah.
conjecture about the trace of Frobenius on this category of nilpotent sheaves is exactly automorphic forms, automorphic functions, I should say. So that was the thing that was proven in that.
So this isn't yet proven, automorphic.
What's that?
Automorphic forms being equivalent to R gamma boxes.
No, this is conditional on this conjecture. I mean, you can take this. I mean, if you want to, one point of view you can take about this whole business is you can say, well, I don't care about this categorical versions, all of that. Forget all of that. I only care about classical Langlands, maybe for function fields. Already, this tells you like a purely spectral description of the space of automorphic functions. Here is a conjectural answer. You can just take this as is as a conjecture of what a precise formulation, the entire space of automorphic functions, exactly supported automorphic functions in terms of something purely built in terms of Galois representation data.
And there's no number field analog of this.
So, well, that's obvious no. So I don't know. I mean, that's something that's certainly a tantalizing thing that one wants to have. But it's not something that exists yet. I mean, there's kind of versions of the, so this work of Bart Schulze is doing some version of this kind of thing for the local Langlands, for the classical local Langlands. But for number fields, you're asking about the global version. Yeah. No, so
It's the same problem. Because don't really,
Yeah.
things can't fuse.
yeah. It's still the same problem. Yeah. That's
F1 doesn't exist.
Yeah, all of these things.
Do they have a version of geometric Laplace conjecture?
Who?
But functions.
Yeah, and that's a version of. You should really think of it as this kind a version of this statement.
Well,
In the
I think
local.
the categorical.
No, but you see, this is the global version. So the way that the structure here works is that the local version is inherently one categorical level. So the local version of everything I'm saying, the local version of that conjecture would be some equivalence of two categories. That's the natural. That kind of level statement. So the analog of this statement would be an equivalence of categories. Because local Langlands is like the category of local of representation of chaotic representations is the same as some other category. So it's naturally It's not about, it's really not about homomorphic functions, it's about homomorphic representation. Those form a category in themselves. Yeah, I guess that's the work of, Gate-Square and Raskin. Have some strategy in general, but it seems to only actually completely works, at least so far for GLN. Which is, essentially to deduce this conjecture from the, deRham version in characteristic 0. That's how that strategy works.
So that in turn depends on the entire sort of in progress.
Yeah, yeah.
100 pages. Hundreds of.
Well, for GLN, it's easier. For GLN, it's easier. That one. And what else to say? I guess even in characteristic 0, you can bootstrap from this to deduce an equivalence of the 3 different versions. You can see now you can kind of formulate. I didn't formulate the other 2 versions of geometric language in characteristic 0, but there's a Betti version and a deRham version, and you can kind of use this restricted version to interpolate. And with some work, one sees that all 3 versions are actually equivalent with the complex numbers.